My name is Aliaksei Sala. I'm lead software engineer. I've been programming in C++ over 10 years. And one of the things I love about C++ is how it gives me opportunities to work on a huge range of different projects. In my case, it's creation of dosimeters, chargers for electrical vehicles, microservices for cloud systems, and software for AI accelerators. In most of the projects, we do care about performance as a C++ developers, but it's like high-level optimization techniques. For instance, do not copy objects if you can move them. But I was always curious about low-level optimization techniques. And we all know the principle. Do not pay for what you do not use. I've already paid for my CPU, so I kind of must use it. So I decided to dive into HPC high-performance computing topic and share my journey with you. So I chose matrix multiplication for this talk. The application of the algorithm is really huge, but during the session, I would like to pick just one, large language models. We're not going into details how it works, but I would like to emphasize that most transformer compute, about 70–90%, we spend on large matrix multiplication, basically in self-attention and feed-forward network. And if we take a look closely on the self-attention, we can notice how heavily we use matrix multiplication here. So it seems like reasonable to optimize matrix multiplication and understand how we can achieve the peak performance for that algorithm. Why peak performance? Let me show you the table where we can see the AI breakthrough people made by past 10–15 years. And we can notice how we started with AlexNet, which required 3 teraflops of total compute, and how the demand for the compute grows over the past 10 years. We go from teraflops to petaflops. Nowadays it's exaflops, and the next it's like a zetaflops. I never thought that I'm going to mention that suffix in the presentation. And since we have this huge demand on the compute, I believe it's really important to achieve the peak performance. And according to OpenAI data, the compute which is required to train a new model double every 4 months. And I'm super excited to see what the next generation of model capable of. So that's the reason why I believe that we need to understand more how to utilize hardware resources more efficiently. So let me introduce the agenda for my talk today. I start with the C++ implementation, the naive implementation, where we can observe in different materials. Then I evaluate the performance. My focus will be on the execution time mostly, and also I'm going to show you the percentage of the peak performance we got for the specific implementation. Then we proceed to the next optimized version of the matrix multiplication, where I apply one of the techniques, and we compare the implementation I show you in the, for example, slide with all previous implementation, and see how we are progressing from the naive implementation to the most performant one. For this particular talk, I used Google Benchmark to run all of my benchmarks, all tests on a Linux machine. I used a quite old CPU. It's an Intel 60 i5 with Haswell microarchitecture. And I compiled my matrix multiplication implementation with the following compiler flags, like O3, fastmath with the specified architecture. Some background context. So I assume that you are familiar with some hardware fundamentals like SIMD instruction, cache memory, stuff like that. I'm going to mention briefly, but I'm not going to dive how it works. In my particular case, matrix is basically vector of double aligned on CPU cache line. In my specific case, it's 64 bytes. Elements are stored in a row major orders, and I'm going to perform dense matrix multiplication of square matrices with the fixed dimension. And the size of the matrices I choose to exceed last level cache. So I would like to achieve peak performance. So let me give you a definition for my presentation. What is the peak performance? So this is how I calculate it for my CPU. I take number of cores, multiply by the base frequency of my CPU, and multiply by floating point operation per cycles my CPU can execute. And in my specific case, I have 4 cores. I tested on the frequency 2.8 gigahertz. And to be able to understand how to calculate floating point operation per cycle, we basically can handle 8 elements per instruction using SIMD instructions. And multiplier 2 comes from the instruction throughput. It basically means the CPU can execute 2 instructions at a time. And we got our peak performance around 180 gigaflops for this specific CPU. So let's begin with our implementations and start with the naive one. So naive matrix multiplication looks really simple. We need to take every row of matrix A and multiply by every column of matrix B. And the result we are going to put into the element of matrix C. It's a pretty simple triple loop, and this implementation I even seen in some GitHub repos people use. Let's measure the performance. Execution time takes 152 seconds. In that table, we can see not just execution time, but I also show the relative speed up, where I compare the next implementation with the previous one. Absolute speed up is a comparison of the current implementation with the naive implementation. Gigaflops, it's how many gigaflops this current implementation executes, and the percent of peak performance, basically it's a fraction of the peak performance I calculated on the previous slides. So the first optimization is changing loop order. So in naive matrix multiplication implementation, we kind of go in an alphabetical order, like over I, J, and K indices. But it's not the very efficient way in terms of data access pattern. So just changing the loop order to the I, K, and J, we can dramatically increase the performance of our algorithm. Some reasoning behind that. So if we take a look at naive matrix multiplication implementation, we can see that when we iterate over I, J, and K indices in that specific order, we access elements from matrix A sequentially, which is good. But we access elements from matrix B with a huge stride, which has really bad spatial locality. And some reasoning behind that is the following. Then when we read an element from the matrix, we don't read just one. We read several elements to populate the whole cache line. So when we're accessing the one element, we basically, let's imagine read 4 of them. And if we don't use all of them, we basically waste our cache memory. And the second reason, why iteration with the huge stride is bad is that it's disable hardware prefetcher. So it becomes much more harder for the prefetcher to retrieve data from memory to the cache. When we change the loop order to IKJ, now we can see that when we iterate over matrix B, we have a sequential data access, which is good. Since matrix A does not depend on the J index, we just reuse the same element when we multiply the elements between A and B, which is also good. And when we iterate over elements of matrix C, we also have sequential data access pattern. And when we measure the execution time, we see that speed up is like 12.6x time faster than the naive implementation. But it's still relatively slow compared to the percent of the peak performance we have. The next optimization is tiling. So let's multiply not elements by elements, but divide matrix into the blocks. And all of these squares, let's imagine it's not an element anymore. It's a block of elements. So for simplicity, our block can contain 4 elements. And tiling algorithm will calculate not just one element from matrix C, but the whole block. And in that particular case, we reuse not just one element from matrix A, but the whole block. So we basically increase data reusage using this optimization technique. Then we iterate over the whole row of matrix B elements to calculate the whole block of matrix C. And to be able to implement this optimization, we just need to add 3 more loops. So the most inner loop will iterate within the block or tile, and the outermost loop will iterate over blocks. Most inner loops I'm going to put into the specific function, which I'm going to refer as kernel. And this is our kernel for naive matrix multiplication. If we measure the performance, we see that we triple the performance compared to the previous implementation using tiling optimization. The next optimization is vectorization. Few words about it. So when, for example, we do the scalar addition and try to sum few elements from array A with few elements from array B, we basically need to execute 4 operations. With SIMD, it's not the case. We can load all of these elements into special vector registers and apply only one operation to get the same results. So this is what we're going to do with our matrix multiplication algorithm. But before we start vectorizing our implementation, let's check the assembly we got from the compiler. And we can see that compiler kind of already used the SIMD instruction for us. So it's kind of know what we're going to do. And one of the interesting things I noticed, then when I moved the most inner loop into the separate function, the assembly changed dramatically. And that version actually is faster. So let's change our naive implementation with the vectorized one and compare after vectorization with manual vectorization. And this is how manual vectorized kernel looks like. This implementation actually, first time I saw in the article what every programmer should know about memory. Highly recommend, I really like it. But it's quite old, so the Ulrich Draper used 128-bit CMD instruction. My CPU support 256 bits, so I just little bit updated that implementation using not the modern instruction set, but a little bit more modern than the previous one. And explanation how it works. So we take the element from matrix A, we broadcast the value to the whole register and put it into the register, let's call it A register. Then we take the whole line from the matrix B, load this, let it be 4 elements into B register. Then we load elements from matrix C into the vector register. And we apply the CMD instruction, which is called fuse, multiply, add, which basically do the two operations at the same time, multiplication and addition. The result goes to the C register, and then we basically store the result back into our matrix C. So this is how vectorized kernel works. And if you compare the assembly generated by the kernel, which we implemented manually with vectorization optimization, with the kernel which compiler vectorized for us, we can see one particular thing, that the compiler does not use all available registers my CPU has compared to the manual implementation. So in that particular case, it's like YMM registers, and we can see that compiler barely used 3 or 4 of them. And in manual implementation, we managed to use all of them. In my particular case, it's 16 registers. So if we measure the performance, we see that it's slightly better than the tiling, 1.23. So the next optimization is cache-aware implementation. And before we jump into it, let me briefly review the memory hierarchy. So on the top level of this pyramid, we have the most expensive, the most performant, and the smallest memory. On the bottom of the pyramid, we have hard disk, which is the biggest one, the slowest one, and the cheapest one. And to be able to explain how we can utilize memory hierarchy and apply it for our matrix multiplication algorithm, I'm going to use the image created by Robert van de Geen, who is a professor of computer sciences at University of Texas. So let's have a look at the first loop around microkernel. We can see that when we multiply all elements from a row of matrix A to the column of matrix B, the first loop around microkernel iterate over rows of matrix A. So that means that we are reusing the tile or block of the matrix B with all of these rows from matrix A. Since we are reusing the B tile all the time, it's most frequently accessed data, so they highly likely will be in the L1 cache. That gives us information how to estimate the size for the tile of the B. So basically, the whole tile of the B must be fit into the L1 cache. If we take a look in the second loop around microkernel, now we reuse the whole block of the matrix A with multiple tiles of matrix B. So now we are reusing the whole block of matrix A. So this will be like the next frequently accessed data. So applying the same logic, this kind of block will go into the L2 cache. And knowing the size of the L2 cache, we can estimate the block size for the matrix A. Following that logic, and depends on the memory hierarchy, we can estimate tile sizes for different blocks for different hierarchy of the memory. How will it impact our implementation? So now instead of 3 loops, outermost loops, we have more to utilize all available memory hierarchy. Instead of 3, we have like 5 now. The outermost loop will iterate over blocks, then within the blocks we iterate over tiles, and then over tiles we basically do the matrix multiplication within the kernel. And here I use NC, MC, and KC to denote the size of the cache blocks, and NR and MR to denote the size of the register blocks. How it affect our kernel implementation? We basically, instead of using the fixed size of the blocks, now we use the sizes we calculated based on the image with the memory hierarchy. And let's check the output of the assembly. Now we can see when we start using these tiling techniques, applying the memory hierarchy, assembly also changed. And now we are not utilizing all available registers anymore compared to the previous implementation. And this is the example of it. But if we measure the performance, we still see some improvements. 1.16 times faster than previous implementation. But okay, we know that we can do better. Let's give a hint for compilers how many CPU registers we have and try to utilize all of them. So how we can do that? The way how I did it, I just manually created amount of C registers, B register, and A registers. So in my particular case, I have 16 registers total. So I allocated 12 registers for C elements, 3 registers for B elements, and 1 register for A elements. These numbers basically I took from the previous implementation in assembly we saw. And now we see much better picture. Now our implementation uses all available CPU registers. So how it impacts the performance? This is the example that we are using all available registers. And we see that we almost double the performance compared to the previous implementation. The next obvious optimization is multithreading. So we have multiple cores. Why we don't use them yet? For this particular CPU, I've tried different approaches to parallelize loops. I tried to parallelize multiple loops on different levels, like top level, nested loops. I pinned specific thread to specific cores, like different techniques. Everything I've tried give me almost the same results. I didn't see any performance improvement. So for this particular case, I decided to go with the simple one. I just split the matrix C over the I index, like row indices, and every thread handle a couple of rows from this matrix. And for my 4-core CPU, it's triple the performance compared to the previous implementation. The next optimization is matrix tile layout. So if we take a look into our kernel, we can notice that we are iterating over matrix A and B with the huge stride. And we all know that it's not really good. Can we do that using just stride equals to 1? And yes, we can. How we can do that? In that picture, that image basically shows us the data access pattern for matrix A. So what I did, instead of accessing elements with this data access pattern within the kernel, I moved this onto the higher level outside of the kernel and copied the data using this data access pattern into the buffer. And then this buffer goes into our kernel. So our kernel now don't need to do the strides when iterating over different elements, and data access will be sequential. And implementation slightly will be different. Now, instead of these huge strides, we have strides which is equal to the size of the register blocks. These numbers are pretty low. For NR it's 12, for MR it's 4. And compilers are happy to unroll these loops for us. And we can see that we basically do not have these inner loops anymore. We just have one loop over K index. And this particular optimization gives us I see I have two rows, 1.17 plus 1.10 speed up. I don't know why I didn't remove this one. So CMD. We already use CMD instructions. But in C++26, we have two CMD library. So I decided to see what will happen if I use this. And this is how the kernel with CMD library looks like. And the most amazing part, it just works. I just replaced all of these scary intrinsic functions, used the SIMD data type, and used like a regular operation like addition, multiplication. And it's like a zero overhead abstraction. The performance remains the same and just works. Really love it. The next optimization is loop unrolling. So let's take a look at our kernel implementation, most inner loop. And we already seen that compiler unrolled the loop for us. But I would like to do that manually and see if it can impact the performance anyhow. So on the left-hand side, we see the original implementation. On the right-hand side, we see, let's say, top of the part of the unrolling. And when we do the manual loop unrolling, there is a problem with that. We don't have this flexibility anymore to change our amount of registers we have. For example, if I change the constant and R, which basically gives us information how many B registers we need to use, it's not flexible anymore. We cannot just change the constant and automatically regenerate amount of B registers we're going to use. So we kind of need to generate a code based on this constant. And there is a way how we can generate such a code and don't do the manual loop unrolling by like writing that code manually. And I used the pack from C++, fold the expression, and built in comma operator to generate unrolled loop. So how it works? Let's imagine we have a simple function print, and we would like to call it 4 times. What we can do? We can implement a new function which is call print n times. Use periodic arguments idx. Use folding expression to expand this call whatever amount of times we need. In our particular case, I passed 4 numbers for that. It's not really convenient, especially if you have not just 4 numbers, but like 32, for example, or even more. So we can use some helpers from C++ standard library, like make index sequence, for example, which generate this sequence for us. Let's use this trick to generate the most inner loop for our kernel implementation. So this is how compute kernel function can look like. So we have index pack, which I called I, which basically unrolled the loop over I indices, and parameter pack J, which unrolled the loop over J indices. So in that particular case, we basically generate a couple of numbers of registers for B, and then we generate a couple of calls for compute row function. And compute row function also use these techniques and basically do the matrix multiplication for us, multiplying elements from matrix A with elements from matrix B. This is how the API looks like. It's a little bit wordy. We can simplify it a little bit by providing function overloading, and I skip this one. and use this compute kernel with make index sequence functions as an implementation details. And the final version of the function will look like that. We just pass our register tile sizes into the compute kernel function, and it will generate unrolled kernel for us. And we are going to do the same trick with storing elements from register C to the matrix C. We create a function store row, which basically execute load inc store function several times. And we create a function store kernel, which executes store row several times. And this is how the store kernel function can be called. In the final implementation of the kernel, which do the loop unrolling manually for us, looks like that. One of the benefits that we automatically support all data types. It's easily customizable. We can generate different kernels with different parameters by passing different template arguments. And if we compare assembly generated by previous implementation with the one we just see when we did the manual unrolling, they almost look the same except one instruction, broadcasts. After unrolling, this is the first instruction in the loop. With manual unrolling, this is the fourth instruction in the loop. Does it make any difference? Yes. It's slightly improved the performance, like 1.02. But I still like to see the improvements. It's super hard to understand how compiler do the basically reorder the instruction in assembly, and it's even harder to impact that. It's just lucky that I have this example. Okay, the next optimization is prefetching. This one, the most difficult to argue about. So basically, except hardware prefetcher, we also have a way to execute the command which prefetch data from the memory to cache. I experimented a lot. I got lots of different controversial results, but at least one thing I noticed that prefetching elements from matrix C gives slightly better performance. And the final result gives me slightly better performance, like 1.07, compared to the previous implementation. And I'm going to compare my result with the OpenBlast implementation. And when I execute the OpenBlast implementation, it's better than mine. Like it's even 1.08% faster than my implementation. So there is a room for improvement. When we reach the peak performance or near peak performance, it becomes hard to reason about the performance itself. So, couple of reasons for that. Like there is no point in analyzing C++ code anymore. So at the end, most of the time, I just check the output of the assembly language. Analyzing instruction for slowness doesn't lead to the same conclusion as we analyze functions in C++. When we see that we have a bottleneck for one specific instructions, when we do the computation, sometimes like fixes with changing data layout can help us. Nothing we can do, for example, in that particular case. So we have a bottleneck with FMA instruction, but the way how we improve the performance, we just applied like tile optimization technique. Instruction level parallelism, it's super difficult to utilize. So like when I did like manual loop unrolling, we noticed that one instruction changed the place in our inner loop, but how to give a hint for compiler to do the best instruction reordering, it's hard to understand. Moreover, I've noticed one interesting case where we can see that in that particular case, the change of the register you are using in your assembly can impact the performance. And I believe this is the hardware bug where when you use RCX register, the CPU cannot utilize register renaming optimization technique. And when the guy changed the RCX instruction to E6, it gives like slightly better performance than the RCX register usage. This kind of fixes we cannot do in C++. Data analysis. It's also not super straightforward. So usually when I use a couple of tools, I use perf, I use vtune to analyze the performance. This is the result from the vtune utils. And on the left-hand side, we see the my implementation. And on the right-hand side, OpenBLAS. So most of the numbers are better for OpenBLAS implementation. So we basically can conclude that OpenBLAS implementation must be faster. But when I use perf, for example, it's not so obvious anymore. Like when we compare the last level cache misses, I have better utilization than OpenBLAS. But when we, for example, compare the instruction per cycles utilization, OpenBLAS does a better job. So it's hard to say just watching this number what implementation will be better in terms of execution time. Then when we use perf to analyze instruction for slowness, like on the left-hand side, we see lots of red instructions. It's basically our bottlenecks where we spend the most of the time. On the right-hand side, the picture much better. We don't have these red lines anymore. And what I did, I just unrolled k-loop, which I didn't touch. It seems like it should be better, but actually the performance remained the same. We just hide this like picture from our eyes. And the most controversial example I got is this. On the left-hand side, we see the implementation which have better characteristics compared to the implementation on the right-hand side. And on the right-hand side, it's an OpenBLAS implementation. So what did I use for the left-hand side implementation? You never believe. It just SIMD implementation, which utilizes 180-bit instructions. It's much, much slower than OpenBLAS. But vtune show me microarchitecture usage, and all of these numbers kind of better than OpenBLAS implementation. But actual result, like execution time, much better in OpenBLAS. So this is what I got. So how effective is C++ for matrix multiplication? When I studied the subject, I learned a lot from different libraries we have, Cocos, BLAS, also learned a lot from different articles when people implement matrix multiplication for GPUs. I really love that we have the zero-cost abstractions with templates, const expr, and I will show you how actually benefit us a little bit later. More power on the horizon. So I demonstrated how SIMD really good at that. Like zero-cost abstraction works perfectly good. I'm playing with MDSpan right now. The thing I really love about it that now when I do this matrix repacking, changing the layout, I can basically check the matrix dimension on a compile time. I really love it because when you implement the matrix multiplication, sometimes you like head blowing and you start forgetting some stuff. You want help from compiler, and MDSpan helped me with that. Stud executor can help with the different strategy for multithreadings. I also will mention a little bit later. And for those who don't want to implement matrix multiplication, we will have stud linear algebra. And C++, like powered by a strong and active community. On last CppCon, I learned so many information, really useful information, which helped me to prepare this talk. But all kernels I observed, they are written in assembly language, and I kind of can understand why people do that. They probably don't want to struggle against the compiler, especially when you need to reorder the instruction. They don't want to depend on specific compilers or version because let's say the performance depends on the compiler. And when I compile all of my implementation with GCC and all of my implementation with Slang, I saw like a dramatic difference for some implementation. But the final implementation behaves the same for Slang and GCC. So this no difference with highly optimized version. And the bug with the hardware, when you need to use, instead of E6, you need to use RSX register, you just cannot do that in C++. So you need to use assembly for this kind of fixes. And as I mentioned, like for some implementation, the performance vary by up to 40% for not optimized, fully optimized matrix multiplication. But I didn't answer the question, how effective is C++ for matrix multiplication? I recently bought a new desktop workstation. It's AMD Zen 5 microarchitecture. So I decided to check how my implementation behaves on the modern CPU. This is our peak performance. Use the same formula I provided at the very beginning. And I got 2.9 teraflops of the peak performance. But I read that CPU will downclock to 3.8 gigahertz if we are using AVX 512 heavy workload. Therefore, the maximum performance, we can use like 3.8 gigahertz to estimate our peak performance for this particular case, and it will be 1.95 teraflops. And when I execute OpenBLAS implementation versus my implementation, I was really surprised. My implementation actually beat OpenBLAS for doubles. And I did what I did, I tweaked tile sizes because my new CPU has different cache sizes, different amount of registers, so I must recalculate all of these parameters. And I also changed the multithreading strategy. So instead of splitting only by row, I start splitting like by blocks, and it will give some also improvements in terms of performance. So in my particular system, 32 threads, so I split the matrix into 4 by 8 grid. Yep, probably. Okay, I will mention it. So 32 threads, but actually CPU has only 16 cores. And this implementation still not utilized the thing that every core has 2 separate threads. So this implementation can be improved by utilizing that information. So all my previous experiments were with doubles, but we got float support for free due to the templates. And we can see that OpenBLAS implementation have the same performance like mine. So here almost no difference. But in C++ 23, we have bfloat 16. And since we get the type support for free, I decided to check how my matrix multiplication will work with the new type, bfloat 16, which is frequently used in large language models and on GPU computing. So compiler cannot efficiently generate assembly when I use bfloat 16. So we have like a special instruction set for this type of data, which compiler didn't use. So I basically created a few specializations for my kernel just to utilize these instructions. And this basically template specialization can be removed when compiler can do the job in the future. So it's like a temporary solution. And unfortunately, I cannot compare with OpenBlast because OpenBlast does not support bfloat 16 right now. So I got 3.09 teraflops of the performance. It's less than float, but still, we basically got this for free. I do nothing. I just, instead of double and float, use bfloat 16. So when I compare with the last, not the last, but with then compare the matrix multiplication performance in Zen 5, I noticed that we kinda at the same level. So I believe that C++ can deliver assembly class performance on matrix multiplication. And my implementation, I believe it's not the best one. I still think that it can be better. So this is all I have. Thank you so much for your attention. And now, if you have any questions, please feel free to ask. Yes, we have a mic here.
Perfect. Thank you very much for the talk. Very interesting. Very
You're welcome.
thoughtful. So you have OpenBlast, but you have also MKL to compare to. Did you compare with MKL, the Intel MKL library?
With MKL, everybody asks me, but the problem is there is one more library which is called BLIS, B-L-I-S. I read the article with benchmarks there, and they showed that the performance of that library on AMD CPU dramatically, like it's much worse than on Intel CPU. So basically, MKL library behaves really good on Intel CPUs, but really bad on AMD.
Yeah. Wait for that. Yes.
Yeah, so
but your hardware was Intel in one case.
Huh?
Your hardware was Intel in the first case.
But unfortunately I didn't measure because I was focused on the...
Okay, fair enough. Okay, so another note, I'm developing a library for multidimensional arrays that the goal is to provide all these abstractions that you had to put manually. I mean, in some sense you are using MDSpan now, but the idea is to give even more abstractions that MDSpan can give you, and so we should talk later. Thank you.
Great. It would be nice to catch with you.
Just a curiosity. I noticed you said that the memory was aligned,
yes.
But in the intrinsics, I saw you using store and load unaligned.
Yeah, exactly. I believe I tried to use align instruction and I didn't see any difference. I tried.
Okay. That's just my...
Yeah,
just my
good observation. Thank you so much.
Hi, great talk.
Thank you so much.
Yeah, you had mentioned using MDSpan. I was wondering what abstractions would make it easier to use MDSpan for this case where you have a lot of compile time dimensions. Did you find that you needed to build more abstractions? Are there things that you would want to have in future versions of the C++ standard library?
So I still think about abstractions. I don't have answer yet. I'm going to try to, because with MDSpan, what I've already tried, like I remove all these pointers from matrix implementation and use MDSpan only. That's good. Like everything was inlined, no performance impact. Then I tried to use customization point, which is layout, and compiler cannot optimize that, and performance much worse than I expected.
Was it reducing to layout stride when you took slices?
I created custom layout because I not just stride. If you remember, it's like I need to iterate over columns, then jump to the next elements of the row. So it's like it's not just a stride; it's like a Z pattern.
Yeah.
So I basically implemented that data access pattern as a layout. Yeah.
Do you think there's still room for that to be optimized in your custom layout, or
sure?
Or is there something that's missing in the standard, maybe?
So what I'm working right now, multi-threading strategy, utilizing of the thread hardwares. And I didn't mention, but it's like when you have fixed dimension of matrices, you don't need to handle tails.
Right.
So I'm trying to address these issues first, get the full picture.
Okay, I understand.
Then I believe it will be much more easier to see what the abstraction can work.
Sure. Well, feel free to reach out if you come up with
Thank
something.
you so much.
Yeah, thank you.
Thank you for the nice talk. The results we have shown and the implementation seems really good. The question is, the CPU you was showing us was a mobile CPU. That is not really good for number crunching. So what was the second CPU you compared with?
Last CPU I used?
Yes.
It's AMD 9950X.
9950X. But is this a server CPU or is this still a desktop CPU?
No, desktop CPU.
Okay, good. So 2 remarks here on HPC computing. The first thing they're doing is they disable hyperthreading because that blocks your maximum performance throughput. And when you are on a desktop, you still have the GUI and so on. So that also takes away a lot of computation power. So you should really test on a cluster Linux machine with no GUI enabled at all.
Yes, that's the good comment, but unfortunately, I tested not in a clean environment. So in the background, there were lots of Linux processes. In general, yes, I need to have this clean environment. But
because other programs pollute your cache and so on, and that's.
So what I also noticed when I use highly optimized version, they don't have lots of impact from, for example, browser. But naive implementation, for example, the performance dramatically change when some process happens under the hood. But highly optimized, they don't jump in terms of performance too much.
Okay.
They jumping there is a range, but
so it didn't got this from the slides. So your first thing took 17 seconds. So how much time you had for the last implementation?
Sorry, could you please repeat?
Yeah, just have the last overview. That's on there. I missed that. The overview of your performance results, the last one.
Would you like to see the table?
Yeah, the table.
This one?
Okay, so your execution time is now below 1 second. That gives you a jitter again. So that's then maybe a measurement problem again. Because the first execution time is quite long, 152 seconds.
Yes.
That's okay, then you have such effects. So the last one is quite low.
Sure, definitely.
And you should increase your test size.
Test size?
Yes, for the last one, the size is too small.
I had such, I didn't provide, but I increased the size of the matrices to see if I have the same performance in terms of gigaflops at least. Yeah.
Okay. Yeah, sorry for the long question marathon.
Very good talk. Two questions. First, when you did Unroll and Prefetch, your custom implementation, how did you assign the parameters, by how much to unroll, and also the prefetch distance?
Prefetch distance. So for prefetch distance, my reasoning behind that, if I'm using the element, I would like to prefetch the next cache line. This is the main reason. Or for matrix C, for example, since I do not copy the elements from matrix C into the buffer, I need to iterate with the huge stride over the elements of matrix C. So here also I do the prefetch with the huge stride, which is equal of the dimension of the matrix. So this is the two places where I...
And for the unroll, by how much to unroll?
How much?
When you did the custom unroll, by how much to unroll the loop? How did you decide that? You just full unrolled everything?
Not everything, just 2 inner loops over I and j index. So over k, I try to unroll just to see if it has an impact. It doesn't. It just shows me a beautiful pair of stats where there is no red instructions, but in terms of execution time, it remains the same.
And then second question is, have you tried different versions of compilers and what's the different performance?
All the time, especially for the last one, because I needed to use mgspan, I needed to use bfloat16. I needed to use SIMD library. So you need to like, use different libraries, different compilers to satisfy all of this like requirements. Right now, I believe I stay with GCC because GCC supports everything. But during the experimentation, I use different compilers, and also check like different version of the compiler if like any degradation or improvements. I didn't notice anything.
I see. But like quantitatively, was a difference in performance you saw between different compilers? Like what's the...
Yeah, so as I mentioned, some of the implementation which is not optimal, GCC sometimes outperforms Silang significantly, and vice versa. For another implementation, Silang outperforms GCC significantly. I don't know why. Like, didn't dive.
But like number-wise, like what's the order of like significantly?
30%.
30%. Okay,
Yes.
Thank you.
You're welcome.
Really excellent talk. Thank you.
Thank you.
Just a conceptual question. When you were talking about the tiling technique, reminded me of convolutions and image processing. So do you think your progression of, progressive optimization, would it change if the case was different and you were dealing with images, or how would you think about that?
So could you please repeat your question?
Yeah, just I guess the question is, if you were to optimize just the tiling technique or starting point because you're dealing with images, would this change how you thought about adding progressive optimizations if you were handling images? Yeah, you're kind of stepping through different ways to optimize.
So
yeah.
You mean if you just pick one optimization technique and apply for your particular case?
Yeah.
Yeah, it should definitely help.
Okay.
Yes.
Okay.
So actually, these orders, I also kind of spent quite time to understand in which order to show you, because this is not the order I implemented in semantics. Yes.
I see.
It's just like one of the random order I decided to demonstrate all of these optimization techniques, but you can reorder the way how you apply these optimization techniques and you still will get the improvements.
Oh, okay. Yeah, thanks.
You're welcome.
Actually, if I may add on to that a little bit, I mean, convolutions work a lot like matrix multiplies, as you probably already know. And so at least we think of it in similar ways and apply similar sorts of optimizations. But there, maybe the difference is the way that you translate it into a matrix like the tiling for cache or the tiling for thread block is kind of the same approach, but maybe the way that you load in the tiles and store the tiles is a little different. And our hardware has some support for convolution specifically, and other hardware may not, so you may have to think about how you're loading it. And in particular, if you use the IM2call approach for convolutions, you're doing extra memory movement in order, like you're replicating data, and so you have to think about how to deal with that. But yeah.
Thank you.